Hello students, good evening everyone. I hope you are getting the voice clearly. Let me check the latency. Yeah. So now I will explain briefly what is Bio-Savart law and a few applications of it. Specifically, how to find magnetic field due to a straight current carrying conductor and how to find magnetic field due to a circular current carrying conductor. Okay, yes, let us go ahead now. Yes, guys, yes, Satavish Gupta, how are you? Yes, good evening, and I just try to let us spend few minutes in revising all these points related to Biot and applications once again, and a few numericals also. Let us try to. Yeah. Biot law. What is this Biot law and what is the use of it? First thing, we'll see the use of it is used to determine magnetic field due to a current carrying wire or current carrying conductor. Current carrying wire or current carrying conductor. And the shape of this current carrying conductor, here we consider two different kinds of shapes. One is a straight current carrying conductor, another one is a circular current carrying conductor. And one more application we discuss afterwards, not in this session, is a solenoid. How to find magnetic field due to a solenoid by using Biot law, also we discussed briefly. So before going ahead with this, we have to recollect back just a simple point, a concept called the sources of magnetic field. We know in your lower classes you have studied that the magnetic field can be produced by a bar. Okay, and if you bring a magnetic needle near this, it will deflect. Okay, and we have discussed some different basic points about this that magnetic field lines start from north pole and ends at south pole, and outside it the magnetic field lines travel from north to south pole outside, and they will not end there, and they travel from south to north inside, and hence they will form a closure. They will form what form magnetic field lines form closure loops in this way. So bar magnet is one of the sources. Lower classes that current carrying conductor produces magnetic field. It was established by an experiment called Iron experiment. If you have a current carrying conductor, yes, it produces magnetic field. He has taken some magnetic needle. So by using this, he has he has observed that this magnetic needle is kept just beneath the current carrying conductor. It is deflecting. Okay, it is deflecting. From this, what he has concluded that is a current carrying conductor is producing a magnetic field. Due to that magnetic field, magnetic needle is deflecting. That's what he has concluded. Right. And the another source of magnetic field is a moving charge. If you have a particle of charge q which is at rest, it produces only electric field. But when it is projected with some velocity, so we call it as moving charge. In addition to electric field, it also produces magnetic field. So a moving charge produces magnetic. The another chapter called electromagnetic waves, we study that instead of projecting this particle with a constant velocity, variable velocity, increasing velocity if you project. That means if the particle is moving with acceleration, then it produces a moving charge with acceleration produces electromagnetic waves. Electromagnetic waves means that is nothing but what carrier of both electric and magnetic fields. Electric and magnetic fields. Okay, electric field, magnetic field, variable electric and magnetic fields it possesses. So that we are not entering now. So we have to just understand that moving charge is one of the source of magnetic field. That's what just I can keep in mind. Now, our interest, we just focus a little more on the second application. Second point here is that is current carrying conductor and as a source of magnetic field. So Biot law deals with this. What it says is, if you have a current carrying conductor, as shown in figure like this, if we have a current carrying conductor, this guys, let me see this. There is some I'm not getting the line. It's continuously stop streaming. Students, are you getting this whiteboard? Someone can drop a message. Are you getting the board screen whiteboard? Drop me a message. Are you able to see the whiteboard? Okay. Yeah. Okay, guys. Look. So Biot law says magnetic field due to a current carrying wire is given by this. And according to this Biot law, if you have current carrying conductor, to find the total magnetic field due to this at a given point, we have to divide this into a few identical small current carrying elements. Current carrying elements. Here we come across one small point called current element. Actually, the product of current and the length of the small element will be called as current element, guys. Current element. It will have a direction. So we represent this as IDL vector. So current element is a vector. Current element is a vector whose direction will be along the direction of current. Along the direction of current. This you have to keep in mind, guys, as a note, as an additional point. Okay. Now, so Biot law says the magnetic field due to a small current carrying element of length dl at a point P, which is at a distance r from the element. When you draw a line from the element to the point, and the line makes an angle theta with the current direction, this angle theta. Then Biot law says that the small amount of magnetic field dB, produced at a point P due to that element is observed to be directly proportional to the current passing through the element. So whatever current passing through the same current passes through the element also. So that is the first observation. Next observation says the dB, the small amount of field produced to the element, is directly proportional to length of the element. dl is length of the element, and it is also taken into consideration that dB, the small amount of field produced, is directly proportional to sine of the angle between the line joining the element and the point and the current direction theta. And it is also considered as this dB is proportional to or inversely proportional to square of the distance between the point and the element, that is dB proportional to 1 by r square, dB proportional to I proportional, dB proportional to dl, dB proportional to sin theta, dB proportional to 1 by r square. And combining these factors, we can write it as dB proportional to IDL sin theta by r square. Here, by replacing this proportionality symbol, we will write it as dB is equal to mu naught by 4 pi into I by r square, and let us consider this as equation 1. Equation 1. This gives the amount of field or magnitude of a field produced by the small element of the dl at a point p, which is at a distance r. This gives only the magnitude of the field. But we know if any field, whether it is electric field or magnetic field or gravitational field or any field, we usually will be treated as a vector quantity. Vector quantity means that should possess both magnitude and direction. Here equation 1 gives only magnitude. So to understand the direction of this, we have to write this Biot-Savart law, this expression in terms of vector form. So the vector form of Biot-Savart law, vector form of Biot-Savart law, vector form of Biot-Savart by 4 pi into I dl vector cross r cap by r square. So dl vector cross r cap, if you consider it in the form of a vector cross b vector, is equal to ab sin theta form. You can write it as dl into magnitude of r cap is 1, so dl sin theta. So then we will get mu naught by 4 pi into I dl sin theta by r square. But you can write here r cap is the unit vector of the point. It can also be expressed as the vector by its magnitude. Okay, because of this, it is nothing but unit vector. Vector by r cube. So here it is plane containing them. So in this way, we will get this one. Okay, so you can take this as equation 2 as the vector form. Equation 2 is the vector form of Biot-Savart law. Equation 2. Where in this equation 2, the proportionality constant mu naught by 4 pi. Mu naught by 4 pi is called as proportionality constant, mu naught by 4 pi. It is given as, the value of this is given as 10 power minus 7 units. And what is the unit of this? We have to say from equation 2. Just a second. Yes. See here, mu naught by 4 pi is a proportionality constant. Its value will be taken as 10 power minus 7 units. To understand the unit of this, from equation 2, you have to write units of all other quantities, and you have to just write a simplified form unit of this. So from equation 1 or 2, you can understand that, because dB is equal to mu naught by 4 pi into I dl sin theta by r square. Sin theta gives you a new number. Current I is current and dl is length. So ampere meter by meter square, will get ampere field should be Tesla. So and hence unit of mu naught by 4 pi is Tesla meter per ampere. Tesla meter per ampere. So here you can write this unit is nothing but 10 power minus 7 Tesla hyphen meter per ampere. So ampere inverse or pi ampere also you can write. So similarly, from this you can write the expression for mu naught, where mu naught is called permeability of free space. Permeability of free space, 4.10 power minus 7 units. Here again, so mu naught can be expressed, the unit of mu naught. Here you can write the unit of mu naught is as from this, here you can say Tesla meter per ampere. Tesla hyphen meter per ampere or by ampere. By using the units of this, you can also write the dimensional formula. Writing dimensional formula of different quantities is very, very, very important. Okay, yeah, guys have to try how to write the dimensional formula also. For writing dimensional formula, this expression may not be useful, but in the later stage of this chapter, we come across force acting on a moving charge. From that, we can write the dimensional formula of this mu naught, permeability of free space. Permeability of for magnetic field, and hence for mu naught also. Okay, so that is how we can do it. That we will discuss later on. Now, so briefly, a few important points about units and dimensions of magnetic field. Units and dimensions of magnetic field. You can pause and you can write down these important points. You can go ahead. Okay. SI unit of magnetic field can be taken as Tesla or Weber per meter square. Weber per meter square unit will be considered from the expression magnetic flux that we'll discuss later, phi is equal to B into A. Just like electric flux is electric field into area, magnetic flux phi B is equal to B into A. From this you can write magnetic field B is equal to magnetic flux phi B by A. For SI unit of magnetic flux is Weber and unit of area is meter square. So SI unit of magnetic field can be expressed as Weber per meter square. This will be drawn from this. Tesla, this is named as a, this has given a special name. Tesla is denoted by capital T. Weber per meter square is denoted by WB, okay, by meter square or hyphen meter per minus 2. So SI unit of mu naught, you guys have to remember this also. SI unit of mu naught is Tesla meter per ampere. Tesla meter per ampere. By knowing the unit of B only, can write here from Biot Savart law only can write the unit of mu naught. Okay, SI unit of mu naught is this Tesla meter per ampere, and the direction of this magnetic field is given by, because we are expressing it as a vector product or a cross product, right hand thumb rule or right hand palm rule. Actually, we prefer right hand palm rule because it gives the easy representation of the direction. Right hand palm rule. So better write down what is this right hand palm rule also, guys. Right hand palm rule. Here only just I will give when the statement for this. Right hand palm rule. Right hand palm rule. So right hand palm rule says point where you want the magnetic field. So I'm repeating again. If you stretch the thumb of right hand in the direction of current and stretch the fingers of right hand onto the point of consideration, or simply onto the point, then the palm, direction of palm gives direction of magnetic field. Then the direction of palm means just so I'll give you one simple example to understand this. Write down completely this first. Then the direction of palm gives the direction. Then gives the direction of magnetic field B. Direction of magnetic field B. See, to understand this, you can consider one simple example. Few simple examples. Here only I will give. You can write the statement, guys. You can write the statement. Pause the screen and write the statement. Pause the screen and write the statement. So here only you can write some examples so that you can understand clearly. This right hand palm rule is very, very important in understanding the direction of magnetic field in different applications. Okay. Pause the screen and write down this. Then you can note down few examples to understand this right hand palm rule. Right, you see here. So an example, let us say. So for write the direction of magnetic field in the following cases. The direction of, or draw the direction of magnetic field in the following cases. Draw the direction of magnetic field in the following cases. First case, we have a horizontal wire. In this, current I is flowing from left to right, from A to B, something like this. Due to this, what is the magnetic field at a point above the conductor at point P, you can say. So what you have to do is you have to stretch the thumb in the direction of current, that is from A to B. The fingers onto the point B, then the palm will be facing our right, facing us, facing you. That means magnetic field will be towards you. As palm is facing you means palm is towards you. So magnetic field will be facing you. So that means outward. Here at this point, magnetic field will be outward. That can be represented with the dot symbol. Dot. Whereas second case, for the same current carrying conductor at a point, if the point P is downwards, then to find the magnetic field, we have to stretch the thumb in the direction of current, and we have to stretch the fingers of right hand onto this point. So here, don't try to curl the fingers around the conductor. So try to take the what do you call the right hand thumb in the direction of current by by showing the palm direction into the plane of the paper, not outside the plane of the paper. Then it will be difficult for you to stretch the fingers onto the point. So then if you stretch the thumb in the direction of current by facing palm into the paper, and that here the magnetic field will be into the plane. As a third case, if you have a current carrying conductor in which a current is flowing into the plane like this, current is flowing like this, then due to this, at a point P, if you want to know the direction of magnetic field according to right hand palm rule, stretch the thumb in the direction of current, means into the plane of the into the plane of the paper or into the plane of the screen. Then stretch the fingers of right hand onto point P. Then the direction of palm will be vertically downwards like this. So this will give you the direction of magnetic field. Whereas as a fourth case, if current is flowing out of the paper, out of the screen like this, then due to this, at a point P, if you want to know the direction of magnetic field, you have to draw a line and now stretch the thumb in the direction. Current is out means you have to stretch the thumb accordingly out of the paper and then line. But in what direction? Perpendicular means left or right. Here, according to this palm rule, it will be right towards right like this. Stretch the thumb in the direction outward direction from the page or screen, and then stretch the fingers onto the point. You can make this is point P. Very you can mark P only. Okay, or PQR is something like that. Then the direction of field will be given by like this. This is how we have to understand the what you call right hand palm rule and how it is giving the direction of magnetic field in different cases. Right, now let's go back to the Biot law and how to find the magnetic field in different cases. Let's go back. Yes. Magnetic field is due to straight current carrying conductor. Magnetic field is due to straight current carrying wire or conductor or current carrying conductor or current carrying wire. Now, yes, see here. So what you have to just understand here is you have to consider this conductor and here step by step we have to do, guys. Step by step we have to do. So the same thing I will explain step by step. So you can consider like a straight current carrying conductor and a small element above the perpendicular line. Here, if you want to field here at a point P, you have to draw a perpendicular line to the conductor. The small element you have considered below this at a distance of y, So this you can consider below or above also. Either way you can consider. Here, so we have considered a small element of length dy at a distance y from this perpendicular line. Here. Okay, if you see the diagram, the diagram you can draw just freshly for understanding purpose. I'm giving here, guys. Okay, here separately just I have mentioned. You can see here as part of that. That's part of that. So this is, see here, this is the conductor. Due to this, at a point P, this is a point P, we want magnetic field. So draw a perpendicular line from the point onto the conductor. At its distance, let us mark it as D. And draw a line from the top end onto the conductor. And the angle made by this with the perpendicular line we are marking as alpha. And draw a line from the bottom end to the point like this. And mark the angle made by that line with the perpendicular line as beta. This is beta. Then consider a small element of length dy at a distance y. For understanding purpose, the same thing is redrawn here. You see here. So we have considered this is a small element, okay, at a distance y. And if you draw a line from that small element onto the point P, and if you mark the angle made by that line is theta, theta or phi, any symbols we can use, theta, then small amount of magnetic field produced by that small element can be taken as dB. So from Biot-Savart law, it is given by dB is equal to mu naught by 4 pi into I into dl. dl is length of the element, that we have taken as dy here. So I into dy into sine theta. Sine theta is nothing but angle between the line drawn from the element to the point and current direction. From symmetry, if this is 90 and this is theta, this will be 90 minus theta, and this is the angle between the line and the current direction. This is nothing but 90 plus theta.